Okay, Chemistry 3101. This is Chapter 11, which deals with synthesis. In essence, this chapter is really a review of chapters 7, 8, 9, and 10. So it mostly covers the content in chapters 7 through 10 and all the different reactions that we learned in all of those chapters. So we're just going to start off by talking about one-step synthesis. Now, one-step synthesis, that's just a politically correct way of saying just a single reaction. And we've learned lots of single reactions throughout the course of the semester. For example, it says here, solving a synthesis problem, providing the reagents, right? That's something you're going to be asked to do a lot in this chapter. Is I'll give you a starting material and I'll give you a product. And you have to decide, what reagents would I use to solve this problem? Now here we're taking an alkene and we're making a vicinal dibromide, alkyl dibromide. So we're going to need to use bromine, and of course that proceeds through the bromonium ion. And but either way, in this case, stereochemistry isn't a consideration because we don't have any chiral centers in the products. But anyhow, this is the kind of thing that you have to be able to do, is to be able to provide the reactions. Now there's some information here. It says you have to master all of the reactions and the reagents required before tackling multi-step synthesis problems. You're going to hear me say that probably a few times today, is you have to master these reactions. Now, students will sometimes ask me, do you have a plan, or do you have a, what's the word I'm looking for? Do you have a strategy that, works for everybody in terms of memorizing reactions? And the answer is absolutely not. I would say there's no one size fits all method of memorizing reactions. But when we look at a problem like question 11.1, this problem covers all of the reactions, or pretty much all of the reactions that we learned in chapter 8. Not all of them, but most of them. And you should be able to solve this problem quickly, right? All of these reactions are just one-step syntheses. Now, of course, some of the one-step syntheses require more than one reagent. But again, you've got to be rock solid on all of these different transformations. Let's start with this one over here, and we'll walk our way through all of these. We'll go clockwise. So if I take an alkane and I want to brominate that, I want to brominate an alkane. Well, you can see that there's more than one type of hydrogen in methyl cyclohexane. And so if I want to do a selective halogenation, of course, I'm going to choose bromine over chlorine, and we discussed that in chapter 10. And so the reagent that you would use would simply be bromine and heat or light. I'm going to put H nu to represent electromagnetic radiation. Well, next, if we want to take that tertiary alkyl bromide and we want to do an elimination. Now, we want to make the most substituted alkene. We want to put the double bond here. We don't want to put the double bond here, right? We want to make the most substituted alkene. And so I'm going to use an unhindered base like sodium methoxide. Now, if you want to write sodium methoxide, that works fine too, but you just have to put some kind of non-hindered base. Again, if you were to take this molecule and if you were to treat this with potassium T-butoxide, okay, potassium T-butoxide, which is usually written in our book, I think, like this. There's a few ways to write potassium T-butoxide, but that's neither here nor there. So if we treat that with a hindered base, like potassium T-butoxide, in that case, we're going to get this molecule here, which is called methylene cyclohexene. And we're going to see several examples today where we have to choose between a hindered or a non-hindered base. All right, well, let's keep moving around here. What about this reaction here? If I want to take that alkene, right, that's what chapter 8 is about. It's about alkenes. If I want to take that alkene and I want to do an anti-Markovnikov addition of bromine, I'm going to have to use HBr, right? I need my hydrogen bromide and I need my peroxides. And we covered that mechanism in chapter 10 as well. We said, okay, well, you have the initiation that comes from the homolytic cleavage of the peroxide. Then you end up forming the bromine radical, which adds to the alkene to form the most stable radical, and then we get the hydrogen abstraction after that. So we covered that reaction in detail. The next reaction is a Markovnikov addition of HBr across a double bond, and so we're simply going to use HBr, right? That's a Markovnikov addition. Nothing really new there. If we move over to the next one, you see that we're starting with, just a simple alkene, and we're ending up with a bifunctional compound, a compound that's got two functional groups. We've got a ketone and an aldehyde in the same molecule. And the way that we end up making those carbonyl functional groups is by cleaving the double bond here, right? The only way that we know how to do that is to first treat the molecule with ozone, O3, And then in the second step, we'll treat it with DMS, which stands for dimethyl sulfide. Now, if you look in the depths of our textbook, you'll see that there's another way to do that. Second step, you could also use zinc and water. Zinc and water, either one will work. And if you peruse the solutions manual, you might find both of those as a second step. Okay, so that's called an ozonolysis reaction. The next one, again, continuing clockwise, we have a syn dihydroxylation, right? Both hydroxyls are ending up on the same face of the molecule, right? This is a syn addition of two hydroxyl groups. Well, how do we do that? Well, there's a few ways that we learned how to do that. Things like potassium permanganate, right, and cold sodium hydroxide. But the best way to do that, or one of the most effective ways to do that, and I'm just going to put it here, is a catalytic amount of osmium tetroxide. Then we use N-methyl morpholine N-oxide, or NMO, as a co-oxidant, and I covered that in class with you. So that is probably the simplest way to do that syn addition of the two alcohols across the double bond. If I want to do an anti-addition, right, here's an anti-addition. For the anti-addition, it's a two-step process, right? The first step, I make the epoxide using MCPBA, or if you want to just write RCO3H, that represents a peroxy acid. That's totally fine. I'll put or peroxy acid. And then in the second step, we cleave that with aqueous acid. This is a mechanism that we looked at in detail. Even the cyclic mechanism to make the epoxide, we looked at that in class, and then you end up making that epoxide, and then you pop that open with aqueous acid. The next reaction is the formation of a halohydrin. So we're adding bromine and a hydroxyl across the double bond. The way that we learn how to do that is to put the molecule in bromine, but instead of having an inert solvent like carbon tetrachloride, say, we put the reaction in water as the solvent. And so you end up forming the bromonium ion in the first step, yes, but then water comes in, and the water is going to attack from the opposite face of the molecule as the bromonium. That's why we get the anti-addition. And the water is going to attack at the most sterically hindered carbon. And we went over why that is. It's because it's going to be more comfortable, if you will, or more stable with the partial carbocationic character that is a result of the transition state of the nucleophilic attack of the water on the bromonium ion. Next one, just a bromination, right? If you want to do an anti-addition of bromine across that double bond, you simply treat it with bromine. Now here, you could put a solvent like carbon tetrachloride, right? That's an inert solvent. The book tends to leave these inert solvents out from time to time, and that's totally fine. If you just want to write Br2, I have no problem with that. And of course, you would end up with the enantiomer, just like you would in the last three examples of the dihydroxylations and the halohydrin formation. Next one is a reaction that most students are pretty solid on. It's just taking the alkene and converting it to an alkane. Right, there's only one way that we learned how to do that, and that's to treat the alkene with hydrogen and palladium, and you could put platinum or nickel. Either way, you're going to end up with the same result. What else? The next reaction. This reaction right here, would you guys call this a Markovnikov addition of water across a double bond, or an anti-Markovnikov addition of water across a double bond? What would this be, Markovnikov or anti-Markovnikov? Yeah, thanks, Jonathan. Thanks, Skylar. Absolutely. It's an anti-addition, isn't it? Right? Because, or sorry, it's an anti-Markovnikov addition, right? Not anti-addition. It's an anti-Markovnikov addition. Anyhow, but it's an anti-Markovnikov addition of water across the double bond, and I'm sure that you guys probably have the conditions memorized, that in the first step we use borane and THF, right? And in the second step, you use hydrogen peroxide and sodium hydroxide. But not only is this an anti-Markovnikov addition of water, I just want to remind you that this is also a syn addition of the hydroxyl and the hydrogen, right? If the hydroxyl is pointing down, remember that the hydrogen is going to be pointing down like this as well. And I told you when I showed you this reaction for the first time, I said, oh, in one of the ACS finals, there was a question where you had to, be aware of not only the anti-Markovnikov addition of water, but also that it's a syn addition of the hydrogen atom and the hydroxyl group. All right, next one is just a Markovnikov addition of water across the double bond. There's no carbocation rearrangements to be concerned with, and so we'll just use aqueous acid to do that. Okay, just use aqueous acid. So like I said, I think this covers basically all of the reactions that we learned in chapter 8. There is one that's missing in here, and that would be oxymercuration demercuration, right? Where the first step we use mercuric acetate and in water, and then the second step we use sodium borohydride. That is missing from this question, and again, that reaction will affect the Markovnikov addition of water across the double bond. However, you avoid carbocation rearrangements. Okay, so I think that's really the only one that's missing on here. Another one that we covered, a whole plethora of different examples was the syn dihydroxylation. We talked about using osmium tetroxide and sodium bisulfate and sodium sulfate and all this different stuff, and then potassium permanganate. But I'll be honest with you, I've taught the class long enough to know that most of my students, when they're asked to provide a reagent, will usually use this one, but you should be cognizant of the others as well for syn dihydroxylation. There we go. Are there any questions about this problem? A lot of information here. Mr. Dion is not crazy. He knows there's a lot of information on this slide. Any questions about that? No? Okay. Again, don't be afraid to stop me at any point and say, can you refresh my memory about that reaction? So that covers, again, chapter 8. I kind of went over not only the reagents, but also, I kind of mentioned which ones you need to know the mechanism of, right? Which mechanisms are really important. We keep coming back to the same mechanisms over and over and over in Organic Chemistry 1. What else can I say about this? What are some ways that you could master this kind of content? I find for me personally, writing things down, like repeating the same motion, like writing it down, there's some kinesthetic learning properties or capabilities, however you want to phrase it there. And I tend to learn by writing things down. Now, I know that not everybody likes that. Some other students, I've had really great students in the past who enjoyed making flashcards. If that's something that you might find interesting, you could maybe make 3x5 cards. You can probably buy a pack of them from Jeff Bezos for not much money, right? Repetition is what's going to help you remember all of these different reactions. All right, let's move on to question 11.2. We're only in the second question in the whole chapter. And then after this, we'll tone it down and we'll talk about some strategies. But this question deals with the reactions that you learned in chapter 9. This is the Alkynes chapter, right? If we go back here, this question focuses on alkene chemistry. So alkene chemistry. And now we're focusing on alkyne chemistry. And we spent 2 full days looking at alkyne chemistry. So let's start with the molecule in the middle. And I think a good place to start would be right here. If we want to do a Markovnikov addition of HBr across that double bond, I would write HBr, and then I would specify to the reader that it's only one equivalent, right? That tells me that I have a 1-to-1 molar ratio of the HBr and the alkyne. Next, if I want to add a second molecule of HBr in a Markovnikov fashion across that double bond, now I'm going to use just another molecule of HBr. So here we don't have to be as specific because it wouldn't matter if you had excess or not. You're just going to end up adding only one molecule of HBr across the double bond. Something else I'll say about this reaction here is I touched on this in class, that the mechanism of this reaction is actually not well understood. And there's a really neat figure in our textbook where he shows kind of a proposed mechanism. It's not something that we do a lot in Organic Chemistry 1, propose mechanisms. But Dr. Diaz and we have a book in our office that's called The Art of Drawing Reasonable Mechanisms in Organic Chemistry. So there are plenty of mechanisms that aren't fully understood, but we can come up with a reasonable idea of how these mechanisms occur. Anyhow, what's next? If we want to take this geminal dibromide and we want to form an alkyne, this is, again, a very important reaction for you to know that in the first step, you're going to treat that. Step 1 is with excess, let me zoom in here for you, excess sodium amide, right, which acts as the base. The first 2 equivalents of sodium amide eliminate HBr, 2 molecules of HBr, but then the third one does a deprotonation of the terminal alkyne. So you have to throw in some water at the end to protonate that carbanion that's formed. There's a reaction that isn't included here, isn't there? What if we wanted to do this? What if we wanted to take the triple bond and make the gem dimethyl? For that, or the gem dibromide? For that, I would just write excess HBr. Again, it's not in there, but I think it's important. Okay, what else? Let's take a look down here in the bottom corner. So now we're going backwards, aren't we? Anyhow, so We're going counterclockwise. If we want to take a vicinal dibromide, right? Remember Gemini on the same carbons, twins, vicinal on adjacent carbons. So we have a vicinal dibromide. If we want to take that and we want to convert that into propine rather, we're going to use the exact same conditions that we did for the geminal dibromide, right? The first step is going to be excess sodium amide. Good. And in the second step, we're going to add water to protonate the terminal alkyne or alkynide that's formed. Now, I want you to know these mechanisms for sure. I want you to be able to draw the double elimination and the proton transfer here and here, of course, right? I think you should be able to draw this mechanism as well. Now, this one's not well understood, so I probably won't get you to draw that mechanism ever. But again, you need to know some of these mechanisms, the ones that I just highlighted. Okay, well, what if we want to do an ozonolysis reaction on an alkyne? Just like with an alkene, the first step is to treat it with ozone. Okay, first step is with ozone, and you end up cleaving the carbon-carbon triple bond here. However, unlike with alkenes where we use DMS or zinc and water, here with an alkyne in the second step, you just use plain old water. Now, since we have a terminal alkyne right here, we just have a hydrogen. This part of the molecule here produces carbon dioxide gas, right? That's just good old, CO2. This is just CO2 gas, okay, which is going to just go up into the atmosphere. And in this case, you're also going to produce acetic acid. So make sure you count your carbons carefully here, right? We have 1, 2, 3 carbons in the molecule. We have 2 of them in this product, and we only have 1 of them in the carbon dioxide molecule. All right, let's speed up here. What if I want to brominate the heck out of this thing? Pardon my language, but that's kind of what we're doing here, right? We're taking the propyne molecule and we're adding 4 bromine atoms to it. Well, you can guess that you're just going to have to treat that with excess bromine, right? Excess Br2 rather. Now, if I only wanted to add 1 molecule of Br2 across the double bond, the triple bond rather, what I would say is I would put bromine and I would specify 1 equivalent. Be careful about that. Just tell the reader that you're only using a 1-to-1 ratio of the propyne and the bromine to make this molecule here. All right, there we go. Let's move on, see what we can see here. The next one, hey, here's a cool reaction because we're changing the carbon skeleton, aren't we? Right here in this reaction, the ozonolysis, we were decreasing the number of carbons in the carbon skeleton, but now we're going to increase it. We're going to go from 3 carbons to 4 carbons. Good news. There's only one way that you've learned how to do that in this class. The first way is to do the deprotonation, right, of the terminal alkyne proton, which has a pK of around 25. Treat that with sodium amide, right? 1 equivalent is all you need to rip that proton off. Now, since we're adding a methyl group, we would simply add methyl iodide as our electrophile. Now, if you want to put methyl bromide or methyl chloride, be my guest. No harm in that. But I like the iodide. It's the most reactive. What's next? We'll go over to the hydrogen reactions last. Anyhow, the next 2 reactions are both the addition of water across a triple bond, right? The first one, the one that results in the aldehyde, is the anti-Markovnikov addition of water across that triple bond, which of course forms an enol, right? You know that the first step is to use 9-BBN. And if you want to write R2BH or dicyamylborane, that works for me too. I don't have a problem with that. Second step is to treat it with hydrogen peroxide and sodium hydroxide, right? We end up forming the enol. I'll draw it here just for fun. We end up with this enol, and that enol undergoes tautomerization to form the aldehyde. Conversely, if we take the propyne molecule and we do the Markovnikov addition of water across that triple bond, what are the conditions? We need to have mercuric sulfate, sulfuric acid, there we go, and water, right? And that produces this enol, which undergoes tautomerization to give you the ketone in this case. So again, this is Markovnikov addition of water across that triple bond. Okay, let's take a look at the reduction conditions. Sorry, I kind of ran out of space here on my slide, didn't I? Anyhow, hopefully you can follow what's going on. If we want to take that, so this molecule is called 2-butene. If we want to reduce that to trans 2-butene, we want to use H2, so hydrogen gas, and Lindlar's catalyst. So we'll put Lindlar's catalyst, which is a poison catalyst. And we even talked a little bit about that mechanism. If I want to just take that alkyne and convert it to the alkane, I'll just beat the heck out of it, right? I just treat it with H2 and we'll put platinum for a change, okay? So nothing special about those conditions. And if I want to make a trans alkene, so here I'm making trans to butene, I would use my red pen and I would use sodium metal reduction. So I'll put sodium and liquid ammonia like that. And there you have it. Okay, that's it. So that's pretty much all the reactions that we covered in chapter 9. All right, there we go. So is it just me, Jerry, or is that a lot of information? That's absolutely a lot of information. And again, I don't want to sound like an old person, but you know what? I've earned the right to talk like an old man a little bit. And, you know, the best thing that you can do really is repeat these reactions over and over and over. Maybe you could even print out the slide. Just print out 10 copies of the slide and fill it out, you know, fill it out 10 times in a row. I have a feeling that by the end, you might be sick of it, but you'll know what's going on. Okay. You'll know the reactions. Hey, can anybody give me a thumbs up? And you don't have to answer this question. If you think you're, you know, maybe 80% of the reactions, you're like, you know what, Mr. Dean, I'm pretty confident in those. You can answer if you feel comfortable. Is anybody feeling good about a lot of these reactions? Great, good. I kind of figured that a lot of my students had been studying and, you know, really practicing these reactions. That's great, great, excellent work, you guys. And you know what? It's not easy. It's not easy, is it? It's not easy to remember a lot of different reactions, but this is a skill that can be developed, right? You can develop your memory skills, and it's kind of up to you to figure out what strategy works best for you, because we're all different, right? We're a diverse student body. We have different ways of learning, and you need to find the way that works best for you. And I gave you a couple of suggestions. Well, let's move on to section 11.2, and really the rest of the chapter is just kind of us taking a look at some concepts in terms of different things that we learned about synthesis. So let's talk about functional groups, right? What if we just have an alkyl halide, right? Just a plain old alkyl halide. Doesn't look too exciting, but you know that you can do a lot of different chemistry with alkyl halides, right? You can do SN1, SN2 reactions, E1, E2 reactions, depending on the type of alkyl halide. What if you wanted to take a functional group like that bromine and you wanted to move it around the molecule, right? You want to move it from this carbon that I have highlighted in yellow, and you want to move it, just move it over to that carbon that's highlighted in green. You all know enough about organic chemistry to say that's not that easy. Okay, it's not just, you know, throwing it over there, right? But we know that we could develop a strategy to do that, right? We could do an elimination reaction. We could do the elimination to form the Zaitsev alkene. So this is the Zaitsev alkene. I'll just put Zait like that, right? If you were to treat this with T-butoxide, potassium T-butoxide, you get the Hoffman alkene. Anyhow, if we want to make the Zaitsev alkene, what would we use? Something like maybe sodium ethoxide or sodium methoxide. Then we want to do a Markov-Nikov addition of HBr across the double bond in that Zaitsev alkene. Now, again, if you've been studying your reactions, this might not seem super challenging to you, but these, again, are the kind of things that you've got to be able to do. So if you were faced with this exact problem, so this is the problem that was on the last slide, right? What are the conditions? The first step is to just treat it with sodium ethoxide. Why? Because you know that you're going to end up abstracting this beta proton. You have your ethoxide, and I'll just draw an abridged version of the mechanism here, right? You're going to do the proton abstraction, form the double bond, and loss of the bromide as a leaving group. You form the Zaitsev product. Then you add HBr to it, and I'm not going to draw the whole mechanism, but if you draw the Lewis structure of HBr, you know that the pi bond is going to behave as a base, or the alkene is going to behave as a base and take on that proton, and you're going to end up forming, the most stable carbocationic intermediate, and then of course the bromide will do a nucleophilic attack, right, like that, and you end up with this tertiary bromide. What else could we do if we had the Zaitsev alkene, right? We could go right back to our starting material. I don't know why on God's green earth you would want to do this reaction, but you know what? It's just practicing our skills, right? Doing an anti-Markov-Nikov addition. Again, if you were to take T-butoxide, right, in that case, and I don't want to draw two mechanisms on the same molecule. I think that's really ugly, but you would end up plucking off this proton, right? This beta proton, because it's less hindered, right? And then you would end up forming the Hoffman alkene, and then you do an anti-Markov-Nikov addition. And look at this. Now we put the bromine on this carbon. We've put it on this carbon and we've put it on this carbon. We've moved it all around the molecule. Pretty interesting, huh? And those, again, are the kind of strategies that we need to take to solve synthesis problems. What if we had a hydroxyl? I feel like we don't spend as much time talking about alcohols as we do alkyl halides. So let's take a hard look at this one here. What if you wanted to take this secondary alcohol, our starting material, and you wanted to make the Zaitsev alkene? Well, an alcohol is not a good leaving group, but we learned how to convert it into a good leaving group by treating it with tosyl chloride impurity. Tosyl, again, is toluene sulfonyl chloride. If you forgot TSCl, so if you draw a toluene molecule, then you put a sulfonyl like this and a chloride. You know, if you have a really inquiring mind, and I know that you're all very busy at this point in the semester, but you could look up the mechanism of that reaction. I think it's in our textbook. I might have gone over it really quickly, but anyhow, you treat that with tosyl chloride impurity to make a tosylate, right? A good leaving group, OTS, and then you do the elimination to form the Zaitsev product. You can do a Markovnikov addition of water to make this alcohol, this tertiary alcohol. What else could you do? Again, I don't know why. Maybe you made a mistake and you said, oh, I'm going the wrong way. So you want to go backwards to do an anti-Markovnikov addition of water. We know how to do that with boron and THF, followed by peroxides and sodium hydroxide. Here's that reaction that was missing on that one question using oxymercuration, demercuration, right? If you were to just try to do, if you were to try to treat this, son of a gun. If you were to take this Hoffman alkene and just treat that with H3O plus, right? You would end up forming a carbocation that looks like, I don't have a lot of room here, but you'd end up forming this carbocation, right? And that would undergo a hydride shift. Okay, so that won't work. So we can just cross that out because you'll get a carbocation rearrangement. So there's a perfectly good example of when to use oxymercuration, demercuration. What else? Next one, if we want to make the Hoffman alkene, again, using tosyl chloride and pyridine, but using a big bulky base like potassium T-butoxide, and then boron and THF and hydrogen peroxide and sodium hydroxide to do an anti-Markovnikov addition. All right, let's take a look at another example here, and then let's get through a couple of things here, and then we're going to take a look at a couple of problems. What else? If you want to move a bromine, or if you want to add a bromine and then do another elimination, we actually talked about this today, how you would do simply a Markovnikov addition of HBr across the double bond here. So this is just treatment with HBr, and then you would use a hindered base like potassium T-butoxide in order to do the elimination. All right, to do the E2 elimination. There we go. So, you know, what are the things that we got to take into consideration? Regioselectivity, right? So choice of reagents is very, very important in organic chemistry, right? If you were to treat this with HBr and peroxides, and well, in that case, you get anti-Markovnikov addition, then you could end up with a double bond down here if you treat it with T-butoxide. So there's all kinds of possibilities. Now, again, this might seem harsh, but I got this from Dr. Klein. It wasn't Mr. Dion that wrote this out. It was on a set of slides that he gave to me and any other instructor who uses the textbook. Says you got no chance to get this far unless you can recall all the reagents. All right. So with that in mind, I'm going to skip this slide and get right into some synthesis problems with you here. So this is question 11.3. I encourage you to not look at the answers, and let's see if we can come up with some ideas for doing these syntheses. Where was I? Back here, 11.3. All right, so 11.3a, I'm going to switch over to a blank document here so I have a little more space to work. Okay, let's see here. So this is 11.3a. If we want to take this alkene and we want to convert it to this terminal alkyne, how are we going to do that? All right, how are we going to do that? Well, while you're thinking about that, I'll clean up this triple bond, which isn't the prettiest thing going. There we go. Okay, well, how are we going to do that? Well, the way that I would think about this is maybe using retrosynthetic analysis, and that's going backwards. If you think about, you know, wanting to make an alkyne, you don't have many ways to make an alkyne in this class, okay? Here we look at the number of carbons. We have a total of 1, 2, 3, 4, 5, 6 carbons. Here we have 1, 2, 3, 4, 5, 6 carbons. 6 carbons here and 6 carbons here. No change in the carbon skeleton. Well, let me cut right to the chase. If I had this compound, oops, that's not good. if I had this compound, right, if I had $1 million, if I had this vicinal dibromide, right, I could take that and I could treat it with excess sodium amide in the first step and water in the second step, do the double elimination and end up with the alkyne, right? So then the question becomes, how do I get from here, from the alkene to the geminal dibromide? So I'm going to ask my students, does anybody know what the conditions would be to go from here, from the alkene to the vicinal dibromide? I think I said geminal when I meant vicinal. And it doesn't have to be a fancy answer. You could either unmute your mic or type it into the chat. Don't worry about subscripts. Mr. Dion will know what you mean. Yeah, exactly, Chris. You want to use bromine, right? Just some bromine, just some Br2, right? Molecular bromine, absolutely. You get the the vicinal dibromide. And then in the last step, we already discussed this, to go from the vicinal dibromide to the terminal alkyne. The first step, you're going to treat it with excess sodium amide. And in the last step, you're going to treat it with water. There we go. All right, let's move on to, this is question 11.3b. If we want to take this primary alkyl bromide, so primary is going to be a little tricky. Let's think about this for a second. We want to move that bromine from this carbon, and we want to put it over here. Now, this one might seem a little bit trickier to you, but in terms of retrosynthesis, right? If we think about retrosynthesis, if I had, sorry, I'm having a problem with my MacBook, which I know happens all the time, but if I had this this molecule, which is called methylene cyclohexane, if I had this molecule, all I would have to do is do, just a treatment with HBr to do a Markov-Nikov addition across that double bond to make this tertiary alkyl bromide. So then the question becomes, how do I get from the primary alkyl bromide to this alkene? Well, if this is my alpha carbon here, there's only one type of beta carbon in the molecule. Okay, so there's only the one type of beta proton, and in fact, there's only one of them, right? It's this proton, and you need to abstract that proton via an E2 mechanism to make this double bond. Now, you might be wondering, well, what am I going to use? Am I going to use potassium T-butoxide? Do we use sodium methoxide, DBU, DBN? Well, if you were to use sodium methoxide, now don't write this down because it's wrong, but if you were to use sodium methoxide, right, that's a strong base, strong nucleophile, and you have a primary alkyl halide, you're actually going to mostly get SN2 if you do that, okay? So in order to suppress the SN2, what you would do is you would use a bulky base like potassium T-butoxide. Now in our book, I can't remember if it has potassium T-butoxide or DBU or DBN, right? Because if you take DBU or DBN and you treat it, which are both, strong bases and strong bases of weak nucleophiles, if you treat those with a primary alkyl halide, you're going to end up with exclusively the E2 product. So you could put here DBU, and again, if you want to put DBN, and we went over what those were in class very quickly, you would end up with this exocyclic alkene like that. And then in the last step, you're just going to take it and treat it with HBr like that. So that's really just a two-step synthesis. Let's try another one that I know you're all going to get probably very quickly, I think, which is this one here. If we have this exocyclic alkene and we want to convert it to this molecule where we have the double bond inside the ring. Okay, so what would be the reagents that I would use for this? Does anybody have a suggestion for a first step? I'm willing to take any suggestion. I might not use it, but I might. Okay, I have a student that says HBr. Yeah, that would be a good way to start. Let's see what happens if we do that, Skylar. We'll just throw some HBr on it and see what happens, right? We're going to get a Markov-Nikov addition. And that's 100% correct. There's nothing wrong with that. There we go. Now, if we want to abstract the more hindered proton, right? If I was to pull off this proton, I would not get the correct product. However, if I pull off this proton, I will get this molecule. And so for that, I'm going to have to use an unhindered base. Can anybody make a suggestion? And it's not a trick question. Just throw me a unhindered base that you would choose. Yep, sodium ethoxide. I agree 100%. Sounds good to me. Sodium ethoxide. Sodium ethoxide is a solution, by the way. It's not a solid compound. It's a solution that usually comes in, maybe in THF. I don't remember exactly, but you know, organic chemists love to handle liquids, right? Liquids are easy to handle. You can use pipettes, you can use Eppendorf pipetters, you can use needles, syringes, and all these types of things. So that would work perfectly well. I want to make a suggestion, though, of another way to do this reaction. I'll show you really quickly. There's actually, in terms of atom economy, it's pretty much the same. And if you're wondering what atom economy is, yeah, the book touches on it at the end of the chapter. But if you wanted to do this, there is a really quick and dirty way that you can do this, okay? Just by using nothing but acids. If you used dilute H3O plus, you're going to get the Markovnikov addition to form the tertiary alcohol, right? That's, again, just a Markovnikov addition. But then if you take that alcohol and you treat it with concentrated H3O plus, okay? In that case, you're going to do the elimination to form the more stable alkene, all right? And that's an E1 mechanism. That's a mechanism that was covered towards the end of chapter 7, but it's a really important mechanism. Whenever you have a tertiary alcohol, or any alcohol really, if you just heat the crap out of it with concentrated acid, or just, again, treat it with a really concentrated acid, you're going to make the most stable double bond. Okay, so that's another way to do it. Here you'd have to buy two different reagents, HBr and sodium ethoxide. Here you only need one. You just need some concentrated acid, you dilute it, and you can do both steps. Now look, before we move on, you're going to find that as we get further and further in the class, that there's more than one answer to a lot of these synthesis problems, especially in organic chemistry too. There's all kinds of answers to these problems. So your question might be, well, which one's correct? The answer is, in this case, I would say both of them are correct. Now, I won't spend a lot of time talking about organic chemistry 2 this morning, but once we get into that class, and I know that most of you plan on taking that class, when you get into organic chemistry 2, let's say somebody comes up with a synthesis that's 4 steps and somebody has another one that's 15 steps. Well, which one do you think is right? The one that's the most efficacious, right? The one that's the fastest and wastes the less material. So less steps is preferred in organic chemistry. All right, let's take a look at, this is 11.3D. Again, I apologize for my children who are screaming in the background because there's a delayed start on Wednesdays on account of the pandemic. Kids don't start elementary school, or my kids don't start till 10:40, I think. Okay, so we're starting with an alkane. Can anybody tell me what the first step in this reaction is? This reaction sequence, I should say, for the synthesis. What's the first step if I'm starting with methyl cyclopentane? And it's not a trick. What's the first step if I have methyl cyclopentane? Okay, let me give you a clue, and it's even highlighted in the book. That's right, Patrick, you're definitely on the right track. Okay, hear ye, hear ye. If you're finding this class isn't tickling your fancy, if you're like, well, you know, synthesis isn't really my bag, but I'm trying to stay awake here. Look, hear ye, okay, guys, listen very carefully. Whenever your starting material is an alkane, that's an alkane. What's in the yellow circle? You've only got one option in this class, okay? Hear me loud and clear. One option is all you have. There's only one choice, okay? And that choice is to brominate it. Nothing else. And you're like, well, what about chlorine? Well, chlorine's going to give you too many products. So you've only got one choice, and that is to treat it with bromine, right? So like Patrick says, a halogenation, right? A substitution reaction. So we're going to make one bromo, one methyl cyclopentane, and then to do the elimination, come on, by now, you guys are faster at this than I am. You know, it's just to treat it with sodium ethoxide or sodium methoxide. It's going to work like that. Okay, these are kind of short synthesis problems, but important, right? And a bunch of important reactions for you to know in there. Well, let's move on. Let me find my spot. Where was I? So we solved that question. Now I want to talk about changing the carbon skeleton. Now, I've alluded to that a few times today. We talked about changing the carbon skeleton when we looked at questions 11.1 and 11.2. I have some more good news for you, okay? If you're like, organic chemistry doesn't have that much good news in it, this is good news. Look, if you have to change the number of carbons in the skeleton, you guys, you don't have many options in Organic Chemistry 1. Okay, if you want to decrease the number of carbons, really, you've got ozonolysis and nothing else. And if you want to increase the number of carbons, we really only have the terminal alkyne that we can deprotonate and then treat it with an electrophile. That's really all that we've got, okay, for in terms of changing the carbon skeleton. So if you want to increase the number of carbons in the molecule, you've got one way of doing it to increase the number of carbons. What's that? To take a terminal alkyne, deprotonate it to make the alkynide, and then you treat it with a powerful electrophile. So we're going to do an SN2 reaction like that. And there you go. You went from 4 carbons in this molecule to a total of 7 carbons over there. Again, look very carefully at my slides. For right now, you only know one way to do this, one way to add carbons. So no questions asked. In Organic Chemistry 2, I promise you'll learn a bunch of new ways that are very new and exciting. You know, we'll even get to look at some of them in the lab, which is really great. But for right now, this is all you got. Okay, what about decreasing the number of carbons in a molecule? You've really only got one way. You can do it with an alkene or an alkyne, but that is ozonolysis, right? If you have an alkene like you do here, you have a total of 5 carbons in this molecule. You end up with 4 carbons after you treat it with ozone followed by dimethyl sulfide or DMS. You make formaldehyde and this aldehyde, which is called butanal here. Anyhow, and again, in the future, but this isn't the future yet. In the future, we're going to learn a bunch more reactions to decrease the number of carbons. But again, for Organic Chemistry 1, this is all you got. Okay, so it really limits you, and it's actually a nice thing. When you're learning synthesis, it's a nice thing to be limited by, hey, I've only got a couple of ways of doing this. I only got one way of doing that. With that in mind, let's see if we can do this problem here. I'm going to give you a couple of seconds to look at it. I'm really thirsty. I'm just going to go grab a quick drink of water. Hey, do any of my students have an idea for the first problem? In fact, could anybody, and I know that not everybody might not have a functioning microphone, but if anybody could just unmute their microphone and tell me quickly, how would you do this first transformation?
Use NaNH or sodium and amide, right? Yeah. And then add ETI onto it.
Okay.
And then do the same thing again, but add methyl iodide to it. Right. MEI.
Okay. I wasn't laughing at you. I was laughing because I'm very happy. Okay. Yes. I give that 100. I give that 100%. Okay. I'm laughing out of joy. Okay. When my students get something right, it makes me very happy. Okay. So this is 100% correct. There is nothing wrong with this synthesis at all. Okay. It makes me very happy. So what the student is saying is, and I'll just go over this really quickly. And I know that for some of you, you might be like, you know, Mr. Dion, give me something tougher. But I know that there's other students that need to look over this reaction quickly. So we're going to take a look. All right, this is acetylene. Right, there's 2 hydrogens with a pKa of 25. So in the first step, when we treat that with sodium amide, and I'm going to do an abridged version of the mechanism here, right, we end up abstracting this proton to make acetylide. That's the nucleophile that's produced after step 1. Then the student said, treat it with ethyl iodide. I said, yeah. So if we draw ethyl iodide, right, what are we going to get? We're going to get an SN2 reaction like that. Now you've increased the number of carbons by 2. Okay. Now you've got 1 butyne. Then the student said, do it again, Mr. Dion. Okay, so there's another acidic proton here. You draw the amide, right? I don't need to draw the counterion right now. I end up with, this would be called what? Butylide. Okay, so I take this terminal alkynide, and then he said treat that with MEI, which is methyl iodide or iodomethane. They both mean the exact same thing. I do an SN2, and walla walla bing bang, you've got yourself a beautiful molecule of 2-pentyne. Okay, so again, that's, you know, kind of a quick and dirty version of the mechanism. there. I didn't include all the counterions, but that's certainly suffice. So we have step 1, step 2, step 3, and step 4. Now, one more thing before we move on to the next problem is that the order in which you do steps 2 and step 4 doesn't amount to a hill of beans, as we say in Nova Scotia, okay? It's not important which order that you do that in, okay? You could have added the methyl iodide first, added the ethyl iodide second. Either way, it's going to work. Give me a thumbs up if you follow me on that. An excellent answer. Whoever answered that was great. It's faster than me. Is there everybody follow me on that one, or is there a question about that? Again, feel free to ask me anything about the. Okay, cool, good. I know that I can't see your thumbs ups or immediately. It's really one of the best ways I have to gauge whether my students follow what's going on here. If you were in lab lecture, the last lab lecture on last Friday, we did spectroscopy, and I talked about this molecule in the lab lecture. This is called benzyl bromide. I told the students it's a really strong lacrimator. So if you know the effect that you get when you're chopping onions, the crying effect, well, take that and multiply it by, 1,000 times. Benzyl bromide is horrible. If you drop one drop on the floor, you will have no friends. Okay, everybody will clear the room. Anyhow, I know it because I've done it. Well, anyhow, how would we take benzyl bromide and convert it to this molecule here? So this would be what? 3-phenylpropene is what you would call this. Now, this is a different problem, compared to a lot of the problems that we look at. Let me explain why. Because here you have to make an assumption that you've got a starting material. So if you only need a little 2-carbon molecule, like acetylene, you can assume that you have that at your disposal. Now, I know I've taught the class long enough to know what your next question is, okay? My astute students are going to say, well, how many carbons can I assume that I have, Mr. Dion? Okay, well, I can't really answer that unequivocally. But usually if it's like a 2 or 3 or 4 carbon piece that you need, you can assume that you have it, okay? Something really small. If you try to, give me a 17 carbon molecule and just say, hey, I just found this, in a store, and I only add 1 carbon to it, that I would say is kind of unrealistic. But look, this is the approach we would take. You've got the benzyl bromide. What if you started with acetylene? Again, acetylene is cheap, at least as far as I know it is. You take acetylene in a tank, you treat it with sodium amide, you make the acetylide in the first step. What are you going to do in the next step? You're going to treat it with benzyl bromide. Now, you can write the whole structure out like this. You're going to get a beautiful, SN2 reaction like that. And then you're going to end up with the final product. So there we go. And we'll put the pH to represent the phenyl group. Again, here you had to assume that you had a starting material. And as long as it's a little molecule, you can assume that you have those. And if you're the kind of person who does all the practice problems in the back of the book, you'll get the hang of what I mean by little molecules that you're that you can assume that you have. Okay, there you go. So, how to approach a synthesis problem. The first thing I would do in this class is I would always count the number of carbons in the starting material in the product, which is usually takes a second to just count. If you haven't changed the number of carbons, what have you got? If you have to increase it, well, you've got one way of doing that. If you have to decrease it, if it's an alkyne, you use ozonolysis. If it's an alkene, you use ozonolysis. Change in functional groups, movement of functional groups around a molecule. We looked at that a bunch of times. There's lots of different ways of doing that. And again, the best way to learn this after you've mastered the reaction is to try many synthesis problems. You could get together with a friend maybe over Microsoft Teams or Zoom or whatever you like, And my students were trying to teach me what TikTok was the other day. Anyhow, but maybe you could do it on that. I don't know. Anyhow, a problem like this now, the book, these are David Klein's ways of solving this problem. It really goes through a long and gaudy synthesis here. But look, let's just go through it quickly. Here we have 1, 2, 3, 4, 5 carbons. So we've got 5 carbons in this molecule. Here we have 1, 2, 3, 5, 6, 7. So we got 7 carbons. I mean, come on. You've got one thing you can do. You can do the deprotonation with sodium amide, right? NH2. And then in the second step, if you're adding 2 carbons, okay, if you want to add 2 carbons to the molecule, what are you going to do? You're going to treat it with ethyl iodide, right? So you would treat it with ethyl iodide, okay? But then you have the alkyne. You want to reduce it to the trans alkene. What are you going to do then? You're going to reduce it with sodium metal, right? Sodium metal reduction. and that will give you the transalkene. So we have sodium and liquid ammonia. Now, again, if that was too fast for you, you can look through the slides. He kind of goes through the whole treatment here, talking about every, step all along the way. So this is a 3-step process. You have steps 1 and 2, and then this would be the 3rd step here. 3-step synthesis. All right. Oh, one more thing. This is something I always have a couple students who, struggle with this. If you have individual steps, you've got to provide numbers for those individual steps. If you just say, just throw everything in one pot, sodium amide, ethyl iodide, and sodium, you're going to get a soup, maybe even an accident. So that's not going to be correct. You've got to know how the numbers work, which order they go in. You got to know to number the reaction steps. So with that in mind, let's take a look at some synthesis problems where you can see clearly that all of these problems involve changes in the carbon skeleton, don't they? Now, personally, as your instructor, I like to try to draw all the intermediates with my students just to kind of get the ball rolling here. But if we take a look at this first synthesis problem, we've got a total of 1, 2, 3, 4, 5 carbons here. Okay, then we have 1, 2, 4, 5, 6, 7, 8 carbons over here. Now notice that if we count this way, let me cut those numbers. Now this I'm just numbering the carbons, not in terms of nomenclature. This is just in terms of numbering. Look, if I zoom in, if you number this 1, 2, 3, 4, 5 like that, you can see that the triple bond is between 1 and 2, and the double bond is here like that. We have ways to convert a triple bond to a double bond, don't we? Right? So I've got to add on these 3 carbons. How am I going to do that? What I'm going to do is I'm going to take that terminal alkyne. Here's my acidic proton. In the first step, I'm going to treat that with sodium amide. So let me just redraw the molecule here. So step 1 is with sodium amide. So Na, NH2, my cation, my anion. I'm just going to draw a quick mechanism here. I'm going to abstract that proton. And I end up making the alkynide, right, like that. Okay, then I want to add 3 carbons to it. I'm going to use propyl iodide. So 1, 2, 3 carbons, and then I'll put an iodide. If you want to write PRI like that, that works too. That means propyl iodide. So that's going to do with the SN2 reaction, like this. So loss of leaving group, nucleophilic attack. Now I'm going to end up with this intermediate. So 1, 2, 3, 4, 5, and then 1, 2, 3, like that. Okay, now in order for me to reduce it to the cis alkene, what are the conditions I'm going to use to reduce it to the cis alkene? Could anybody tell me? And it's not a trick. This should be on does not like trick questions, in case you didn't get that after a few months of taking a class with me. What would I use here to make the cis alkene? Yep, Lindlaier's catalyst. Exactly. Thanks, Josh. Thanks, Skylar. Perfect. So H2, hydrogen gas, and Lindlaier's catalyst. Absolutely. If you want to write poison catalyst, if you don't want to write out Lindlaier's and just write poison catalyst, that works fine. In fact, I think in the ACS study guide, if any of you have that, you'll see that sometimes they just write poison catalyst. And yeah, that works totally. All right. Well, let's move on from there. And I think the next question is significantly more difficult. So I made a little space here to solve it. We want to take this alkene here, and we want to convert it to a different alkene. And we're moving the double bond around in the molecule. I want to show you how to solve this one, assuming that you've got some acetylene. Okay, so we're going to have to assume that we've got some acetylene here. Now, the way that I think about this in terms of retrosynthesis is, let's count the number of carbons. I've got 1, 2, 3, 4, 5, 6 carbons here, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons over here. I've got to add a total of 3 carbons. And it looks like they're added over here, right? It looks like they're added on the end. If I had, and again, I'm thinking in terms of retrosynthesis, right? Going backwards here, if I had $1 million, if I had this molecule, that primary alkyl halide, what if I treated that with acetylide, right? I can make acetylide from acetylene and sodium amide, right? And again, I told you, you can assume that you've got small molecules, right? Then I could do an SN2 reaction here, and I would have 2 carbons added, but then I would end up with a terminal alkyne, which I could deprotonate and add a methyl group. If you don't follow me 100% on that, let me show you what I mean. So in order for us to make this primary alkyl halide, what do we need to do? An anti-Markovnikov of bromine across that double bond. So we need HBr and peroxides. Again, sometimes as your instructor, it's fun to review stuff along the way, right? You have the fish hook arrows to produce the most stable radical intermediate. Then you have the hydrogen abstraction. So I'm not going to do the whole thing, but you end up with, excuse me, this guy right here. Now, I didn't look at the solution in the manual, so there's probably a couple of ways of doing this. If you assumed, and I'm going to write this in red because I'm not going to use it, but if you assumed that you had this terminal alkyne, so that you had a 3-carbon terminal alkyne, you could take that and you could do an SN2 reaction, right? And that would give you this compound. So there we go, like that. Yeah, 1, 2, 3, like that. Okay, that would give you this compound, and then you would just reduce it with sodium by sodium metal reduction. But using a smaller intermediate, if you want to use just acetylene, okay, here's what I would do, is I would take this molecule and I would treat it with sodium acetylide. Remember this chestnut? Yeah, we used it a million times in the alkynes chapter. All right, that would do an SN2 reaction like this, and that would end up producing this intermediate, okay, like that. How do you make the sodium acetylide? You take acetylene and you treat it with sodium amide, okay, and that will give you this reagent. Now, in order to complete the synthesis, what am I going to do? I'm going to deprotonate my terminal alkyne by treating it with 1 sodium amide. Then I'm going to treat it with methyl iodide. And then I'm going to end up with an intermediate that has 9 carbons. And take a look where that triple bond is. It's right where we want it. 1, 2, 3. There we go. So now, in order to finish out the synthesis, to go from this molecule to this molecule, I'm taking the alkyne and I'm reducing it to a transalkene. I'm going to use sodium and liquid ammonia. And so when we look at all of these steps, what do we have? Let's tally them up down here. We have step 1 is HBr and peroxides. So that's the first step. Second step is the treatment with sodium acetylide. So we'll just write sodium acetylide like this. That works. Third step is to treat it with sodium amide. Fourth step was to treat it with methyl iodide, which I'm going to write CH3I. It's the same thing as MEI. And then in the fifth step, we're going to treat it with sodium metal and liquid ammonia, like that. So that's a 5-step synthesis. Right? That's not trivial. I don't think that's trivial at all. That'd be insane to say that's trivial. Give me a thumbs up if you follow me on the concept, or if you have a question, feel free to interject. Stop me along the way. Does anybody follow me on this one? Think they could maybe get it? You had a little bit of time to think about it? All right, great. I remember learning this, back in 1995 probably, and I remember really enjoying it, thinking I'm the kind of person that likes puzzles, and I kind of think of a synthesis as a puzzle. Some of the ones I saw in graduate school just seemed like really horrible puzzles, but ones like this are, reasonable once you get the hang of all the different reactions. Let's take a look at another synthesis problem. And I'm going to go through this one a little bit quicker because I want to try to get through a lot of the content today so that next class we can just focus on some practice. This is question 11.7. Question 11.7, and this is E. If we want to take this alkene and we want to make, now we're adding a bunch of carbons here. So we have 1, 2, 3. There we go. And we want to put the triple bond out here. I'm really trying to draw these triple bonds as neatly as I can. Maybe it's not the iPad, it's probably me. There we go. It looks a little better. Okay, so let's tally up the number of carbons. We've got 5 carbons in this molecule. Here we have 1, 2, 3, 4, 5, 6, 7. 7 carbons. So we need to add these 2 carbons onto the end of the molecule, right? You can see how we have these 3 carbons here in that arrangement. So I need to somehow make this molecule. I need to make this where I have a leaving group out here, because then I could treat that with acetylide, right? And I could do the nucleophilic attack and make the terminal alkyne. So how do I put the bromine all the way on the end, right? Well, the first thing I could do is an anti-Markovnikov addition of HBr across that double bond. If I treat this with HBr and peroxides, that's going to give me the secondary alkyl bromide as opposed to the tertiary. But it's still not where I want it. It's on this carbon, oops, that I have highlighted in yellow, and I want to put it on this one that's highlighted in red. So I need to move it over, right? And we've looked at how to move a leaving group around the molecule, right? If I take this and I treat it with a hindered base like potassium T-butoxide, that's going to abstract this beta proton, the less hindered beta proton. If you want to practice your mechanism drawing, you can put in a negative charge here and say, okay, well, it's going to pull off this proton, do the elimination, loss of leaving group, and I'm going to end up with this alkene like that. Then to tack the bromine on the end of the compound, I'm going to use HBr and peroxides again. Okay, then I end up with that intermediate that I have drawn in red in the top right corner. Okay, and now the last thing that we have to do is simply take that primary alkyl halide right here and treat that with sodium acetylide. And there you have it, my friends. You do an SN2 like that, okay, and you end up with your terminal alkyne like that. Again, I think a very reasonable problem if we tally up all the steps. Let's see, we got a total of 1, 2, 3, 4. Only 4 steps for that one, so not so bad. But again, you can see how you've got to have a really solid command of all the reactions that we've looked at in order for you to master problems like this one. Okay, let's go back to our lecture notes here. And we're pretty much, we're getting close, I should say, to the end of the problems. And something that you saw me employ in the last problem was retrosynthetic analysis, right? Going backwards. If you're ever stuck and you don't know how to go forwards, it's always, it will definitely be fruitful if you look at the product and say, well, how would I have made that? Here you have the same number of carbons, right, in both of these molecules. I mean, really, how would you make, if you don't know how to do this, then how could you make that terminal alkyne? The only real, idea that we would have would be to somehow have this molecule, right? Would be to have that vicinal dibromide, do a double elimination. So then you've simplified the problem already. How do I get from here to here? I'm not sure. I don't know. I don't know how to do that. Well, take another step back. How would I make the vicinal dibromide? I know it's not pretty because I don't have a lot of room on my slide here, but the only option you've got is to start with this alkene and then just to brominate it. So then you've simplified it again. How the heck do I get from here to here? Now it's starting to get a little more reasonable, right? If I could convert this hydroxyl into a good leaving group and then do an elimination, hey, then I could end up with that alkene, couldn't I? Right? So that's the way retrosynthesis works. Now, obviously, we're just learning in Organic Chemistry 1, this kind of concept here. So here's the first retrosynthetic arrow to make the vicinal dibromide that I was just speaking about. But researchers in universities, when they want to make, or even people who work in pharma, if they want to make very complicated molecules, and this is usually people who do research in universities, if they're just, trying to synthesize a complex skeleton in a molecule. I've heard that people like Barry Trost, maybe, or, E.J. Corey, some of the greatest organic chemists ever, what they would do is they would draw the molecule in the corner of a chalkboard in their office, and they would look at it for a year. Now, I don't mean they would sit there and stare at it for a year, but they'd have it in their, near them, the structure, to look at every once in a while over the course of a year, and they would come up with all kinds of different ways to attack that synthesis, right? They may come up with 10 different ideas, and then they pick the best one and go for that, to try to make a very complex molecule. So again, going back to this question, how do we go from the alcohol to the geminal dibromide? Well, I said if you had the alkene, right, that would definitely help. And now you've simplified the problem again, right? If we have the alkene, we can simply brominate it. And now it becomes a lot more reasonable of a problem, right? All you have to do is convert that alcohol into a good leaving group. And then since you would end up with a primary tosylate, so I'll draw the intermediate that's formed after step 1. It's going to look like this, OTS, okay? You would treat that with DBU or DBN, which are strong bases but weak nucleophiles. Why? Because you're only going to get E2. If you were to try to use sodium methoxide here, okay, or T-butoxide. T-butoxide, I guess, would work. You'd end up with elimination product. But remember, if you were to try to use sodium methoxide, you're mostly going to get SN2. Okay, so that's not really a good choice. So we'll erase that like that. And there you go. Now you've figured out a problem that I think is not obvious when you look at it. And you got the whole thing, and it's 5 steps. Okay, tosyl chloride to make a good leaving group out of the alcohol. T-butoxide. Oh, I guess I switched it here from T-butoxide. And again, you could put DBU or DBN. Either one of those works. DBN. Yeah, those are all fine. Then brominate it here. They've chosen to show a solvent, carbon tetrachloride, to produce the vicinal dibromide, then the double elimination, then the deprotonation, and then you put water in, and there you go. There you have it, my friends. There you go. That's a really, pretty synthesis when you think about it. All right. So really all we have to cover is are these syntheses. We'll look at these at the start of class on Friday. We're not going to cover the part on green chemistry. If you're the kind of person who's concerned about the environment, the reason we skip this part is not because it's unimportant, but because we don't ask questions about it. However, green chemistry, I think, is important enough that on Friday, I will talk about it a little bit with you. I would like you to have a little bit of working knowledge of what green chemistry is, because it's always a good idea for us to find ways to protect the environment and to mitigate pollution, right? Let's face it, we work with a lot of nasty chemicals and elements in organic chemistry, things like mercury and heavy metals, and we want to avoid using those things if we can. And we're going to talk about ways that we can make our chemistry more environmentally friendly on Friday. I think it's really important for you to just take a quick peek at that with me. And then in terms of section 11.7 is more of an FYI section. It talks to you about making your own synthesis problems. And this is something you could try at home. Is just start with a small compound and then just choose little reactions that you could do with that compound and the products that are formed from it. Then you erase all the reaction conditions and then you try to come up with them. So it's something you could do with a friend maybe. I don't really do this with my students, but it is a good idea to learn how to do that. Okay. And again, as I told you, as we get farther along in the class, you're going to find that there's more and more ways of doing this type of syntheses that we learn in Organic Chemistry 1 and even more in Organic Chemistry 2. So it boils down to finding the most facile synthesis that generally has the fewest steps. And then, of course, if you want to go one step beyond that, then you would take into consideration, trying to have a reaction that's very green, in terms of mitigating pollution